everyone, I am Shikha Yadav from Netaji Subhash University of Technology. I am here to present my presentation on hydrothermal synthesis and characterization of tin telluride. My paper ID is 273. So let us start. In this presentation, the topics that are to be covered are number one, the reason behind this research. Then we are going to discuss the introduction part. And after that, methodology will be discussed. Later on, the result will discuss the result and the discussion part. In the end, the future scope of this research will be discussed. So here we get started. First of all, let me tell the reason why I chose this research. Basically, the reason behind is there are three reasons for that. The 2D dimensional nanocrystal has been investigated widely for their new and improved property. It means that 2D material they have some new property as compared to some 0-dimensional and 1-dimensional nanocrystals. Secondly, if I talk about the properties of 2D metal chalcogenized, such as lead sulfide, cadmium sulfide, cadmium selenium, they have been extensively studied over the past years. But though they have some fascinating properties like electric and optoelectronic properties, but they have some disadvantages, or we can say some limitations. They have high toxicity, which limits their further application. So now our research interest or the research focus has been turned to some other materials in the 2D dimensional. 2D dimensional nanocrystals such as tin sulfide, if we talk about tin telluride, they are emerging among these metal chalcogenized due to their excellent properties and wide applications. For example, if I talk about tin telluride, the reason for its being chosen is it has high sensitivity toward gases like sulfur oxide, chlorine, etc. Also, it has some unique properties like it has a very narrow band gap, which has gained the interest of many researchers toward this particular topic. And also the reason why we usually choose 2D material is that their morphology can easily be changed, which make them good for sensing devices. So let me talk about the introduction part. So basically, the 2D dimensional material has received the attention of various researchers since the James group used the mechanical exfoliation method to obtain graphene. So the graphene has various unique properties like mechanical, structure, optical, and electronic properties as well. But among these array of 2D material, the spotlight has turned to 2D monochalcogenized. The reason is that the graphene-like materials lack some energy band gap limits, which limit their application in the photoelectronic and sensing devices. Whereas if I talk about the 2D transition metal monochalcogenized, they have drawn the interest of numerous researchers due to their wide applications in this photovoltaic gas sensing devices, thermoelectric devices, etc. So next I'm going to talk about the methodology that I adopted in my research. So the process started with dissolving Di, tin chloride hydroxide, and the hydrated hydrogen. These three were mixed in a beaker, and after that, after mixing in a beaker, the beaker was kept on the magnetic stirrer for the 30 minutes. We took another beaker in which the Di water and ethylene was added. And in this mixture, we also added the tin oxide. The tin oxide was added, and again, this beaker was kept on the magnetic stirrer for the 30 minutes. And after that, we mixed the two solution in 1:1 stoichiometric ratio. After mixing these two mixture, we then transferred our solution to the Teflon lined chamber. And after putting this, also we know that the Teflon lined chamber is able to withstand high temperature and high pressure. Therefore, we poured our solution in this Teflon, and then finally we packed it in an autoclave. Since we are following the method of hydrothermal, we used the reason for choosing this method is because it is cost effective, easy to perform, and it takes less time as compared to other methods. So after packing the solution in the autoclave, we kept the solution in the autoclave oven. It was kept in this for at 150 degrees Celsius for 24 hours. After keeping it, after that, it was taken out and was kept for the cooling for 24 hours. The solution was then taken for the centrifugation using DI and ethanol. And finally, we moved our sample to the vacuum oven at 100 degrees Celsius to dry it up. And after that, the sample was finally grinded in the mortar and pestle. And then we got the prepared sample. So this was the methodology that I followed in my research to prepare the tin telluride. So these are some of the formulas that have been used in my research paper. The three formulas like Debye equation, size strain equation, WH plot, these three have been used to find the crystallite size and strain. Other formula that have been used are the band gap energy, crystallite parameter, and the refractive index. These are all things that I calculated in my paper. So let's talk about the result and the discussion. Firstly, I'm going to talk about the XRD. So this was the XRD pattern that I obtained using my XRD data. So these were the diffraction pattern that I observed, and it matched with the JCPDS card number this. And also the pattern that is displayed on the screen is the smooth data. Actually, I got 28 degree, I got a broad peak. And that broad peak showed, it means that it is a semi-amorphous material that we obtained. This material was calculated in the range of 5 degree to 90 degrees and at the position 2 theta. And also the crystallite structure has been shown here. The red dot mentions the tin atom, and the blue resembles the telluride part. So this was the crystallite structure that we obtained, and the latest parameters of this structure were exactly matching with the JCPDS card number. After doing the XRD, we did the Ritwell refinement in order to get to determine the exact position of the atom we got on the crystal sample. So next we'll talk about the WH plot and the size strain. As I said, I used three formulas to get the crystallite size. The number one was the Debye equation, which used this one formula. This D is equals to K lambda upon beta cos theta, where D is the crystallite size, K is the Scherer constant, beta is WHM plot, and this lambda is the wavelength of the XRD. So firstly, I calculated the crystallite size using this formula, and the approximate value was 63 nanometers. The second formula that I used was the WH plot. This was the equation that I used to find the crystallite size using WH plot, and this equation was first equivalent to the linear equation. So this is the WH plot. On the x-axis 4 sine theta and the y-axis beta cos theta were plotted. In this, we got the intercept as this. Using the intercept, we found the value of crystallite size, and using the slope, we get to know about the strain in our material that we obtained. Similarly, I used the third method, size strain method, and using this plot, we were able to calculate the crystallite size and the strain for the graph. The value that I obtained using this were, for the crystallite size, the value obtained was 63.14 nanometer. When I used the WH plot, the crystallite size was 20.1 nanometer, and this much of the strain was observed. And for for the size strain, I got the value 67.8 nanometer, and this much of the strain was observed. Since I used three methods, now the question arises, which size should we rely on? We use three methods. So all three methods have some advantages and some limitations too. Generally, Divisor equation is used to calculate the crystallite size, but a Divisor equation do not consider any defect in the crystal structure. Therefore, we need to use some other approaches to calculate the crystallite size, that is WH and size strain, because they also calculate the strain value, that how much strain is being included in our material. So that's why we used WH and size strain plot to calculate the crystallite size and the strain. After this is the plot that I obtained using the equation mentioned above, the WH plot and size strain. After that, we'll talk about the absorption plot and the dot plot. So in the UV absorption spectroscopy, I used the absorption data and found the band gap also, and various other properties of the material such as band gap, conduction and the valence band, and other properties were found. So firstly, let's see the absorption plot. In this absorption plot, we can see that the maximum absorption is seen in the visible region. These are some broad peaks that are being seen here. So maximum absorption is seen in the visible region. And also using the equation, using the Beer-Lambert law, we calculated the band gap of this was the equation that I used to calculate the band gap, and the band gap, the value that I obtained was 0.185 electron volt. So this was the value that I obtained, and as we know, the standard value of energy band gap for the tin telluride is also 0.18, which makes it a narrow band gap semiconductor, and it has wide application in thermoelectric devices and the gas sensing devices. So lastly, we'll talk about the FESM and the EDX pattern that we observed. So these are the some morphological and the topology image of the sample that we obtained. We can see that some spherical shaped image structure is seen. It means that the crystallite structure was spherical shaped, and the EDX pattern, which is shown here, has some intense peak of SNTE, which shows the elemental composition of our material. The material consists of tin and the telluride, which confirms that the material that we prepared has the tin and telluride in it. So this from this we got the elemental composition, and the morphology was also checked by this. So these are some results. These are the crystallite size and the latest parameter values that I obtained. The calculated value for the synthesized SNTE was 6.3, whereas in the JCS PDS file it was found 6.32, which is approximately equal, which confirms that our the structure that we obtained is accurate. So lastly, I'll talk about some future scope of this research. So SNTE can be extensively used in various fields like IR detection, photoconductivity, or the thermoelectric material. Also, it is employed as a favorable P-type semiconductor in thermoelectric devices. The most important property of SNTE, the reason why we have used SNTE, not the other material, is that it is non-toxic, eco-friendly, and also it is a good alternative to the lead telluride. Because lead telluride is very environmental risk. It is very, and also it should be avoided because it involves environmental risk. So, and also the lastly, the tin telluride has a huge application in the thermoelectric material, and also its unique properties have been emerging, which make that it may emerge as a good, may be used as a good sensing devices. Thank you so much.
Good morning, everyone. I'm Dr. Shivanand CS, Assistant Professor, Department of Physics, Nagarjuna College of Management Studies, Chikbadapur. Today, I'm going to give invited talk on size modification of green synthesized silver nanoparticles under UV exposure and its bacterial resistance. So this is the outline of my presentation, introduction to silk and silver nanoparticles, material and methods, characterization techniques, result and discussion, conclusions and references. So introduction to silk. So silk is an ancient biomaterial. It is extracted from a silkworm, a family of Bombyx muri. So the silk cocoons is extracted from silkworm. So this silk is a very good functional biomaterials. It is used in a textile industry. Nowadays, it is used in many more electronic device level fabrications because it's a very good dielectric materials. And this silk cocoons composition of two protein materials. One is sericin material, another one is the fibroin material. This sericin is coated over the fibroin surface. This sericin is a very gumming material. It's so sticky and it can encapsulate it over the fibroin material. And whereas the fibroin is a very lead, its fibroin is a very shine and smooth uh, biopolymer. It is composition of a high amount of amino acid residues. In figure 2, this is a cross-sectional view of silk fiber. And this silk fiber, it has two blocks. One is the hydrophobic and hydrophilic nature. And due to this, silk is having a silk 1 and silk 2 structure. Silk 1 is a alpha helix structure and silk 2 is a random coil beta conformation. And this figure 4, which shows the primary structure of amino acid sequences in silk fibroin biomaterials. And now, this is an introduction to silver nanoparticles. So we all know that the silver nanoparticles has a very good bacterial resistance, and many researchers are done their synthesis of silver nanoparticles in a wide variety of approaches. And also, this silver nanoparticles is an important inorganic nanoparticles with the particle size ranging from 1 to 100 nanoparticles. And the silver nanoparticle exhibit a peculiar properties known as the surface Plasmon resonance and high thermal conductivity, electrical conductivity, surface enhanced Raman scattering, chemical stability, non-linear optical behavior, well-developed surfaces, and catalytic activity, and also high electric double layer capacitance. And many researchers can afford to incorporate silver nanoparticles in a wide range of medical equipments, including bone treat, cement, surgical suture materials, needles, and surgical masks, etc. Nowadays, the people's coated this silver nanoparticles over many functional biomaterials, for example, silk fibrin, chitosan, and polymethyl methacrylate, and carboxymethyl cellulose. These are very good uh, applications in medical field. So these nanoparticles have their attractive physiochemical properties and biological activities compared with the ordinary metals, so that it is received considerable attention in the field of biomedical imaging using CEPs. So figure 5 is a typical high resolution transmission electron microscope image of biosynthesized spherical shaped silver nanoparticles. Next, there are many approaches for the synthesis of silver nanoparticles, but in our work, we restricted to the synthesis approach for biological methods. So there are many approaches: physical methods, chemical methods, and biological methods. Now, the recent trend, all the researchers are deviated their interest from biological or green chemistry. This is the schematic representation of synthesis of silver nanoparticles. And in our work, we have synthesized silver nanoparticles using a silk fibroin, a functional biomaterial. So it has shown in figure 7. So in this work, we chosen a UV radiation as a tool to increase the catalytic reactions of the composite colloidal solutions. So this figure represents, we take the silk cocoons and we made into a pure silk fibroin solution, and we added the silver nitrate, and we irradiated for different hours of radiation exposure. Then we characterize the colloidal solution. So now this is the materials and methods. We have chosen the sodium carbonate, lithium bromide, and silver nitrate. We purchased from Sigma Aldrich. Pure Mysore silk cocoons were obtained from Silk Culture Department, University of Mysore, Karnataka, India. So this is the standard protocol for the synthesis or preparation of a pure silk fibrin solution. This is a schematic protocol we have shown in the figure. Here, the silk cocoons we cut into small pieces. Then we put into 1 liter of hot water and we heat the beaker for 1 hour. Later, the sericin coated over the fibron is removed because this is the gumming materials. So after 1 hour, we take the fiber, we squeeze it, and we dry it for 2 days. Later, the dried fiber is put it on a beaker and a 9.3 molarity of lithium bromide is added to the cell dried fiber. Then we get the silk fibroin lithium bromide solution. We got in this figure. So later we take the solution of lithium bromide and uh, fiber solution. We inject it into dialysis cassette. So why here we want to do the removal of toxic metal ions present in the solution. So because lithium is a very toxic metal ion, so in order to remove these lithium metal ions from the solution, we did the dialysis. So the dialysis is carried out for 3 days. So later we remove the solution from the dialysis cassette. Later we take the solution and we centrifuged. The undissolved silk will be segregated at the bottom of the centrifuge tube. So now the pure silk fibrin solution is ready for next experimental part. Now, the fixed weight% of silk fibrin solution, for example, we taken here the 5-8% of silk fibrin solution. We added a constant or a fixed known amount of silver nitrate to silk fibrin solution. We made like this. This is a pure silk fibrin solution. Silk fibrin with a known amount of fixed amount of silver nitrate, like that we exposed to ultraviolet radiations. So this is the UV chamber. We kept all the bottles in the UV chamber. The color of the solution is gradually changes from yellow to a dark brown color. So this is the formation of silver nanoparticles in the silk fibrin solution. So this is the schematic representation of synthesis of silver nanoparticles in silk fibrin solution. So later we get the colloidal silk fibrin silver nanoparticle solution. So later the composite solutions we further characterized with the different characterization techniques: UV visible spectra, FTIR, XRD, transmission electron microscopy, particle size, and assessment of antibacterial activity. Here, this UV and XRD, TEM, particle size, all these are the size determination characterization techniques. So we done all these characterization techniques. So now the result and discussion part. So the UV visible spectroscopy. Here the what we have irradiated the sample with the different hours: half an hour, 1 hour, 2 hour, 3 hour, 4 hour, up to 5 hours. We irradiated the samples. So as the time of exposure is increases, there will be a more number of nanoparticles is synthesized in the silk fibrin solution. And also we put it under UV visible spectroscopy. We get a very nice SPR band is observed around 400 to 450, 460 nanometers. So this is due to the formation of spherical shaped sized nanoparticles. This we also confirmed in transmission electron microscopy. So this is the SPR band is observed around 400 to 460 nanometer. And also we observe here the particles, the SPR band is slightly shifted from higher wavelength to lower wavelength. This is due to the formation of small number nanoparticles, small sized nanoparticles also. Next, FTR spectra. So here also this the figure A, figure 12A is a pure silk fibrin graph, and B is a silk fibrin silver nanoparticle composite solution. See here the absorption band is observed 1536 and 1514. This is corresponding to the amino acids or amide groups present in the silk fibroin. And also the hydroxyl group is around 3280 is the presence of hydroxyl group present in the silk fibroin. And there is a difference in the peak. There will be the one more extra peak arised at 1746. This peak is corresponding to the formation of silver nanoparticles, and it confirms, this peak is confirms the formation of silver nanoparticles, because in silk fibroin there will be a tyrosine molecule that can helps to reduce the silver ions into silver neutral atom. So that is the silver atoms. So this is the confirmation by FTIR spectroscopy. And XRD patterns, here also the pure silk fibroin, the diffraction pattern is observed around 20 degree. So this is due to the amino acid residues riding over the silk fibroin surface. And in the next, the red color diffraction pattern, which gives, there will be an additional peak around 111 plane, 200, 220, 211, corresponding to the 38, 44, 56, and 78 diffraction peaks. So this is confirms the formation of silver nanoparticles with the face-centered cubic structure. And also we compare this data with the standard JCPDS files, and it exactly matches. This is a confirmation by XRD patterns. Later, we have done the transmission electron microscopy, that is high resolution transmission electron microscopy, with the different hours samples, the formation of sized nanoparticles. And also high resolution transmission electron
Dr.
microscopy.
Shivananda, please
Yes,
compile your work. You have 1 minute only. Huh?
okay, sir. Okay, I'll finish.
Thank you very much.
Okay, so this is transmission electron microscopy. This is high resolution image of a single nanoparticle. And also this is the interplanar spacing we have calculated using image software. This is the SAD pattern of the diffraction pattern. And also we have done the dynamic light scattering in order to get the stability of the samples, how this composite solutions are more stable in composite solutions. And this is the result and discussion. We have calculated the TEM size and the DLS. The size also we have calculated for the 3-hour irradiation, and this is a zeta potential value. And this is the result and discussion in the antibacterial assessment. So we have done the gram positive and gram negative bacteria. We have calculated the antibacterial property. So this is the standard. We took the gentamicin as the standard, and this is the different hour of irradiation. As the hour of irradiation increases, the zone of inhibition also increases. If the nanoparticle size is very smaller and smaller, the zone of inhibition also more and more. So this is a table shows the antibacterial activity. So for pure 1 hour, 2 hour up to standard. So this is the for 30-minute size, 30-minute irradiation, we get the zone of inhibition is more, because in 30-minute irradiation, there will be a small sized nanoparticles is formed. That's why it is able to kill more than the large sized nanoparticles. So this is a schematic table for antibacterial assessment. And this is a 3D graph for antibacterial assessment. Now the conclusion, in this study, the silver nanoparticles were synthesized by silk fibron under UV irradiation method. The synthesized Ag nanoparticles in colloidal solutions are stable, suggesting that silk fibron extract can be used as a reducing and stabilizing agent. Here, we have not used any stabilizing agent. Silk itself has a stabilizing agent and can convert the ions to nanoparticles. The physical property of biosynthesized silver nanoparticles were characterized by the relevant techniques. Further, we demonstrated the potential application of silver nanoparticles in medical field, as it shows antibacterial activity against human bacteria. So these are my references. And thank you so much. If you have any queries, you can ask.
Hello everyone, I am Shreya from Netaji Subhash University of Technology, and today I am presenting my work on the potential of tin-doped barium hydride for advanced optoelectronic and catalytic applications. So in the present work, I'll give a brief introduction of barium hydride, followed by the synthesis procedure that we used for the synthesis of the material. Then I'll discuss the various characterization techniques that I used to analyze the as synthesized material. And finally, I'll conclude my work. Starting with the introduction part, I'll discuss the properties of pristine barium hydride initially. It usually crystallizes in the orthorhombic structure, as can be seen here in the schematic diagram on the right-hand side. Its melting point is 675 degrees Celsius and its boiling point is 1673 degrees Celsius. It vigorously reacts with water and releases hydrogen gas, and thus it can be widely explored for hydrogen production and storage applications. It has excellent reversibility and good thermal stability. However, there are some limitations of pristine barium hydride, which are it has wide band gap, which is approximately 4.5 electron volts, and it has low electrical conductivity due to high band gap in the pristine state. Thus, it affects its direct use in the electronic and electrical applications. To overcome these applications, I have doped the barium hydride with tin, as can be seen here in the figure. Doping of tin introduces additional charge carriers into the lattice, and it improves the electrical conductivity of the pristine barium hydride, enhances catalytic activity by influencing the reaction kinetics, and it enhances stability also. It increases the storage capacity of the material. And thus, due to these enhanced properties, it can be a promising candidate for optoelectronic and catalytic applications. Now discussing on the applications of tin-doped barium hydride, it can be used in a variety of applications, some of which are shown here. It can be used in hydrogen storage, hydrogen production, catalysis, ammonia production, and hydrogen sensing. Now moving on to the synthesis part, we have used co-precipitation method to synthesize tin-doped barium hydride nanospheres. Initially, we dissolved barium chloride into DI water and prepared the barium chloride solution. Simultaneously, tin chloride was dissolved by magnetic stirring in DI water, after which the later solution was added dropwise into the former solution. The final solution was stirred for a few minutes, after which H2O2 was added into the mixture to change the reaction kinetics. And the pH was maintained by ammonia water to 10. After which the final solution was left undisturbed overnight, and finally it was washed and dried at 60 degrees Celsius to obtain the final tin-doped barium hydride material. Now going on to the results and discussion part, I'll start by the structural analysis of the material, which was done by X-ray diffraction technique. Here we can see the XRD pattern of the as-synthesized material in which high-intensity peaks can be observed. It reveals the crystalline nature of the material. The peaks were matched with the barium hydride of the orthorhombic phase with JCPDS file number as shown on the right-hand side, and some peaks were matched with tin as indexed with JCPDS file number shown here. The lattice parameters of the synthesized material were calculated and were compared with the standard data, and they were found to be in good agreement with the standard parameters. Debye-Scherrer equation was used to calculate the crystallite size, which was found to be approximately 26 nanometers, after which Williamson-Hall plot and size strain plots were obtained using the equations shown here, and using the intercept and slope values of the WH and SS plots, we obtained crystallite size and strain values, which were also found to be in nano region. Then the optical properties of the material were studied using UV spectroscopy. Here we can see the absorbance graph of the material. It shows that the material absorbs in the UV region mainly, with absorbance peak, maximum absorbance peak at 228 nanometers. And using this data, top plot was obtained, using which we found that the band gap of the material was reduced to 4.07 electron volt. The morphological analysis of the material was obtained by field emission scanning electron microscopy. Here we can see nano-sized polyhedral shaped particles, and we can see that as these nanoparticles have high surface area to volume ratio, thus they are good for catalytic applications. Here we can see the EDX pattern obtained along with the SEM, and the presence of tin, barium, and oxygen was clearly shown here. The other peaks were corresponded to carbon and cold coating, which was used to take the images of the material. Finally, moving on to the conclusion part, I can say that tin-doped barium hydride was synthesized via co-precipitation route, and white-colored powder was obtained by the synthesis method. XRD data confirmed the formation of orthorhombic barium hydride and tin of average crystallite size approximately 26 nanometers. UV spectroscopy showed the significant absorbance in UV region with band gap of 4.07 electron volts, as can be seen here. The polyhedral shaped nanoparticles were also observed by morphological analysis. Thank you so much for your kind
So
attention.
my talk today is polymer-based detectors, and let me just tell the audience that these detectors we built in another place, which is TIFR. The students had gone and built them there, and these detectors are based on plastic scintillation material. And I'll give you the detail little later, but you can see in the last picture in this slide, these were being built and they were put up by the students in the institute. And this is the shape in which they have been built. And they have been put in a particular order because this is called a mini array, in where the distance between the detectors and the detector configuration and how it is how it is put on the ground is very important. And as you can see in this slide, the material is polystyrene, which was the solvent, and in that we had put peri-terephenyl, and pop-up was another tertiary fluorescent fluor which we had added. This pop-up is for shifting the wavelength in the region which gives you the maximum sensitivity for the PMT, because these detectors are basically detecting very small quantum field particles from the air. I'll explain that in the next slide. But when these detectors are detecting these particles, the signal is 130 millivolts or so after a PMT is coupled to the detector. And the hut that you see, the top of the hut is the PMT, the photomultiplier tube, which is responsible for collecting the signal, and then it is connected to these wires, which are then from the side they are coming to the lab. So this setup was done recently, and it was completed in 2019 end, and now the data has started coming in. But since the work was going on for the past around now 8 years, so we have been able to do lot many simulations in this area. So this is the process that I was talking of, the air shower, where very high energetic particle from the atmosphere enters the air, and it interacts with generally nitrogen, which is the maximum to be found in the upper layers. And then these particles then decay further into hadrons and mesons. And finally, at the sea level, we are able to get hadronic component, muon component, and neutrino components. Now, hadron component is basically we are not able to detect it at the moment with these detectors, but we are able to see muon component. So we are talking of the muon component. This is the experimental part that I'm showing you. But these are the details of the air shower, what is the electromagnetic shower and how the muons are created. But when we go to the simulation part, which is what we've been doing for quite a long time in the lab, there is a software which is Corsica, which is given by Cascade in Germany. This is a group which gives an open software in which you can simulate the shower. And so we are simulating hadronic interactions, which are not actually possible otherwise. So because the energy at which proton is hitting the detector and the array, that energy calculations are still not available with the LHC also. So we have to take care of Corsica or softwares and then do simulations. So this is an outline of what this Monte Carlo code does, and it is a little bit time taking. It describes the transport, and this was the analysis which we presented in this systems conference, and it is published. This was the analysis for different primary particle air showers. So this is the air astrophysics part, where we are discussing all different electrons, the secondaries, which is electrons and muons. And this is the final detail and the results from our simulations in Corsica, which have got vetted with the parallel simulations from different other groups for different energies. We did it for Agra, where this DISA experiment is situated. So this was done for, and these results are for that. Then we are going to the second application, which was another simulation. This was done in Giant4. Please, I would like to share this with the audience that these have been done by the students, different students. So the previous work was another student. This is a second student, and she had worked in Gianfor, in which we are doing the calculating the stopping power of proton beams. Let me show you the beam, so that will be interesting for the audience. This is a beam which is incident on this water phantom, which is the human body, and this water phantom, we can design different organs in this phantom in Gianfor, and these are different double foil scattering system. These are different scintillation detectors and different other detectors which are needed to be considered in the beam line, because a beam line is not an independent entity. There are many things which are needed to modulate it, excuse me, to modulate the energy of the beam, and to govern or design the spread of the beam in geometrical sense, and then also how to collimate the beam finally where it should fall. All that is done through these different detectors in line. So this is a snapshot of what what we were doing in the simulation, and the results for this was, we were calculating the energy deposited in the water phantom, but this was in the form of a voxel. So voxel means each layer was separate, and we could see where the particle is going and depositing. So the phantom was voxelized in 200 slabs. Then the energy was deposited for both the primary and the secondary particles. It was collected in each voxel, and all this is possible in GAND4. So there are different cuts could be introduced for every particle. How much or to which layer do you want to see the secondary particles produced, and when do you want the secondary particle to die off? In GAND4, it is this language is used. So then the study which was conducted by the student was study the dose curve parameters for tumors in human tissues using passive proton beam. Now in this is the phantom, and in this they had designed, in the next slide you'll see, but here the overall study was these 4 points, which was what is the impact of the inhomogeneities on Bragg curve and its parameters, statistical analysis of the Bragg curve, and determine the Bragg curve associated with the peak, penumbra width, and the range. And then analytical calculations were also done, because the material was designed by the user. So we knew what we were designing. So this is a picture where we have designed, and it was basically the phantom was a 5-year, 10-year, 15-year, and an adult, and the organs were brain, kidney, and thyroid. And how much dose was deposited. So this was basically how much is the absorbed dose which was absorbed, and how much is the equivalent dose which is reaching the organ that we were targeting. So it basically meant that where is the tumor? If it is in this part in the brain, then how much is the dose deposited by this proton beam for the kidney and for the thyroid? And then is it the one which is in value with what is allowed, and how much is needed depending upon the width of the tumor, how thick was the tumor? So all those considerations have been taken, and then this was a PhD, and this is a published work of this student. And the results for this work were that the stopping power of proton beam in different materials like brass, aluminium, copper, water, lead, plexiglass was computed. And then physical distribution of the dose curves were also observed. And these two parameters, radioactive RBE and spread out in the Bragg peak, was also studied. And the details are all given in the published work, which is given in the paper also. The attached paper to the conference. The last which I'm going to discuss is space missions, in which space radiation is a risk for the crew people. And what were we doing in the lab? We were trying to design shielding material. So we thought that let's put a new shielding material, and we tried to do it with polystyrene and two materials which will come later. But then what are we trying to shield the space human is from the galactic cosmic rays, which is very strong, and the trapped magnetic radiation in the field, in the magnetic field of the earth, and finally the solar energetic particles which come out during the solar storm, which is huge. So these were very intense radiations which are being experienced by the astronauts in space. So we were trying to design a shield for these for the astronaut from these different materials. So the shield, the simulation was again done in Giant 4, where one was without shielding and the other was with shielding. And in this, we had taken these materials: aluminum, polyethylene, polystyrene, and water. And polyethylene is basically, polystyrene is the organic scintillator that we have been using in the lab. So we were more interested in this part. So these are the root plots of the simulation which we had done, the student had done. And there are two plots that I'm showing you. First, the energy of the primary, which is reaching the phantom, and second, the secondary particles reaching the phantom. And in this data, the initial energy which was given was this much, and how much is the energy which is reaching these different particles, and how much is the secondary. So what we see is the secondary particles reaching the phantom was very large here, and this was no shielding, it was very less, which meant basically we will the audience may recognize this and understand this more, because that is a little tricky. Polyethylene, the calculated dose was 117, and polystyrene it was 107, and this is what we got in the expected, what we expected from the simulation. So this is basically like telling us that these materials, both polyethylene and polystyrene, the inorganic the organic scintillator, they have maximum number of the secondaries were produced. Now this is also one factor that you should appreciate here, because these two materials were able to break the primary particle into secondaries, and so less harmful, for a much better shielding was there, because it was able to break the primary particle, because the primary particle is the harmful thing. It should not be absorbed by the human body. So even if the secondaries are absorbed, their energy is already reduced, so it will not be a problem. And the more important factor was this, that the calculated dose was a lot, and it was comparable in these two materials. So dose deposition was minimum in these two cases. This is exactly what we wanted. Of course, water is never there, so we were always looking as compared to aluminum, and so we got a very good result, and this was accepted as a publication. I think, yeah, the publication is right here in this PPT. It is in a Springer journal, yeah, here. And this was also published. And so this is the last slide. And this is where we interact with the students in the department, small other students. And this is the Muon telescope we have set up in the lab. This is the electronics. This is a NIM rack. This is the oscilloscope, and this is the CAMAC crate. And these are the collaborations. The detectors were simulated, were actually built in TIFR, Cosmic Ray Lab Ooty. And we have MOU with IUAC New Delhi, and they work with us. And this is the professor with whom we had set up this experiment. These are visitors to the lab, and this is the outline and the picture of the lab. And that's it. I have concluded my talk.
So good afternoon to everyone, and welcome to the conference. So my topic is based on synthesis characterization of sodium niobate-based glass ceramics for energy applications. Myself, Dr. Soum Mukherjee, at present assistant professor at Kazi Nazrul University, Department of Metallurgical Engineering. So this is the overview of my presentation: objective, abstract, introduction, experiment procedure, result discussion, and conclusions. The objective is mainly to develop the sodium niobate-based glass ceramics, and it has been developed by using melt quenching process, and some characterization is done to make it the material fit for as an energy material, because we people are moving.
Just switch on your camera.
Actually, it is getting blocked, I think. Actually, it is getting shared. No, that's why I cannot move out. So, so is it okay without camera?
Just stop right now and then move, switch on. Try to
Yes, please.
just stop the sharing. Then try to switch on your camera. Yeah, is it coming?
Is
Yeah,
it?
yeah, yeah.
Okay.
Okay. Now you share.
Okay. So is it coming, sir?
Yeah, yeah, yeah. Okay.
Okay, so objective is to develop this sodium niobate-based glass ceramics, and it has been carried out by melt quenching process. Okay, and some characterizations done so that we can say that material is fit for energy material. And why we are doing this? Because as we know that we are looking for several alternative materials for our own future sustainable goals. This next is the abstract. I am not going to the abstract since it will be self-explained with the following slides. Now, before moving to the main result discussion and the experiments, now why glass ceramics? Because glass ceramics are some emerging materials, though it is not so new, but still with the advent of material science, nowadays people are moving towards glass ceramics for various reasons. Actually, the glass ceramics are a class of materials which are actually found by controlled nucleation and crystallization within the glass matrix. It is either possible by nucleated agent or without nucleated agent. So if we compare with the composites, it is actually composed of one crystalline phase and one glassy matrix phase, and it will give several plethora of properties, either high strength, low porosity, toughness, stability, chemical durability. Actually, simultaneously we are playing with the vitrification and devitrification process. Vitrification is the glassy phase and devitrification is the crystalline phase, and that will tolerate so many applications. The application are versatile, starting from dental implants, luminescent based materials, high temperature based materials, materials which have controlled friction coefficients for waste immobilization, and so on. Now, generally, people have talked so many on ferroelectric ceramics and so much. So the world have talked of ferroelectric ceramic materials, titanates, niobates, but there are crystalline materials which are meant for sensors, transducers, from healthcare sector to defense to aerospace and other. But when we are clubbing the optical properties with the ferroelectric properties, then the ferroelectric glass ceramics could be a better options, because the ferroelectric glass ceramics have several advantages like low porosity, strength, better dielectric strength, and these property variations could be match up with the coupling of crystalline and glassy matrix phase. And also depending on the synthesis route, we can have several crystalline size options and so many variations. Moreover, the new age photonic materials are also possible with these ferroelectric glass ceramics. Moreover, ferroelectric glass ceramics are easily formable in compared to rigid crystalline ceramics because of its capacity to have to get shaping with the help of melting process. And when we are talking photonics, that means we are having cross effects of electro-optics and all these things. Now let us move to the experimental part. Now how we have synthesized. So it's a very much solid state in nature synthesis where we are taking the oxides mainly, silica, europium oxides, niobium pentoxide, sodium carbonates for the source like silicon, europium, niobium, and sodium for making the sodium niobate based system. That is europium dot systems. The oxides have been taken. They have been motored in agate mortar and pestle for 30 minutes after proper weighing and put in the furnace for melting. We have utilized platinum crucible for melting purpose, and after melting, the molten system is put in a cast iron mold for casting. Now we have to be careful in this stage because we have to release the stress, because that stress may be detrimental. To relax the stress, some sort of aniline treatment is given, and after that it is cast into some dimensions and polished with cerium oxides. The prepared samples were first put for thermal analysis to know certain properties. Then we have done a heat treatment followed by XRD density measurement and more bonding analysis and PL analysis. Now coming to the result discussion part. The first is the thermal analysis. Now, thermal analysis have been carried out at different heating rates, that is 10 Kelvin per minute, 15, 20, 25, 30, 35. And we have noted the corresponding the glass transitions, initialization of first peak, the peak maxima of the first peak, second peak, and the melting temperature. These variations which have been observed, it is mainly due to the changes in the viscosity of the glass melt. The Tg is the change from the melting to the glassy state, and this is and there is some viscosity change, and due to these viscosity changes within the matrix, these values are also changing correspondingly. Moreover, we have also analyzed the activation energy for crystallization developed from the glassy matrix to crystallization leading to glass ceramics, and it has been carried out with the help of Kissinger plot, Ozawa plot, and August-Bennett plot. Following are the equation that have been utilized for Kissinger, August, Bennett, Ozawa, and the values for activation energies are 260 kilojoule per mole from Kissinger. For August, Bennett, it is 269, and from Ozawa, it is 279. And these values are found to be quite less in compared to other glass ceramic systems, and which shows that sodium niobate systems are quite good for having this crystallization within the glassy matrix. And within the same system, if we compare, the Kissinger is giving much lower value. That is Kissinger mode of this linear variation of crystallizations. Now, moving to the phase development. Following this, we have undergo heat treatment to have the glass ceramization. It is very interesting to note that at 703 hours, though there is some small peaks are getting, but it is not that crystalline in nature. It is still showing good hump, that is amorphous. With changes to higher duration periods, say 5 hours, we are getting proper crystalline phase, and obviously at higher temperature, crystalline phase with no other impurities. It is sodium niobate based systems. Obviously, with the change in temperature, actually what happens, the diffusion process get assisted and the crystalline order is getting restored. That is the main changes, and it has been verified from the JCPDS data card. And we have only calculated the crystal size of the 705 hours because we want to have the lowest temperature for crystallization, and we are getting the crystalline size to be 43.8 nanometers, which is close to 44 nanometers. Now, the FTI analysis have been carried out. We have utilized reflectance mode, and we have tried to analyze the metal oxide coordination systems, and we are getting the comparison between the base glass and the glass ceramized at 5 hours and 3 hours. And we are getting the peaks identified at 543 centimeter inverse and 694, which is corresponding to some sodium niobate systems and niobium oxide systems. The peak, which is around 838, it is actually close to silicon oxygen silicon, which is the framework, and within which the crystalline system will be developed. And the corresponding comparisons between base glass and the glass ceramics are also shown. There are slight variations because the base glass is based on the sodium niobate, and it is getting transformed to crystalline. So drastically there is no just drastic change of metal oxide coordinations. It is almost chemical composition is almost same. That's why no drastic such changes are observed. The microstructure is shown for the lowest temperature nucleation for the lowest temperature heat treatment systems, and it is carried for 5 hours, and the microstructure is quite packed systems, and the crystallite size, the particle size are quite big, that is 100 to 300 nanometer, which is homogeneously distributed. It is dense packed structure, which is what rhombic shaped crystallite structure with minimum porosity and interlocked features that have been observed. And one of the most important thing is that to observe the contrasting features within this glass matrix, we have to etch the sample with HF solution. After that, we have carried out the refractive index calculations using prism coupler, and the refractive index of this system have been fitted with Cauchy's equations, and we have founded the refractive index at 5 different wavelengths of 473 nanometers, 532 nanometers, 632.8, 1064 and 5952. It is as per standard, and we found that it is varying between 1.81 to 1.75. And if we observe the value at 632 nanometer, it is close to 1.78. This high value is coming due to the presence of niobium oxide, and which this niobium being a heavy metal being a heavy metal oxide is giving polarizability, which rises the refractive index value. Density have been calculated using Archimedes principle, and it is noted to be around 3.41. Now we have also calculated the optical transitions, and it is carried out with the help of this transmittance spectrum is carried out with the help of EVV's NIR of the sample, and it is in the range from 4000 to 1800. The transmittance are quite close to 75 to 84% in the wavelength region, and these characteristic absorption bands are noted, which are assigned to these transition 7F0 to 5L6 and 7F0 to 5D1 following the Corner's notations. Moreover, the band gap energy calculations of the base glass and the glass ceramic systems have been compared, and it is noted the base glass is having the band gap of 2.88, while in the case of glass ceramide sample it is 2.76. The difference is mainly due to the change from the amorphous to crystalline nature. In amorphous, what happens? The non-bridging oxygen is limited, while in case of glass ceramide, due to the presence of this more crystalline order, the non-bonding oxygen, non-bridging oxygen is become more prominent, and as a result, these changes coming up. Moreover, europium 3+, which are utilized as a dopant, they will also induce some defect states and some FF orbital splitting, and that will also have some impact on the band gap change. Next is the Raman spectral analysis, which have been carried and we have compared with the base glass, and there are some changes which we observed. So these are the strong bands that we have observed. Some bands are not observed in case of base glass, while some are observed in case of glass ceramide systems. This is due to the due to the phonon coupling of the crystallization process, which is assisted with the crystalline process, low phonon coupling. So minor shift in the spectra are noted if we compare the glass ceramides with the base glass. And after that, we have calculated the PL spectra analysis, and the PL spectra analysis showed in compared to base glass, the glass ceramide samples have more intense peak, which is quite intense in nature. And we have obtained two intense bands at 395 and 460, and in addition to that, some weak bands at 364, 383, 416, and 533. Actually, this europium doping is also creating some changes. They are creating some localized changes with field perturbation induced in the host matrix. So in conclusion, we can say that the process that we have followed is successful in creating this glass ceramic process. The glass ceramic development, it is a very common solid state melt quenching process, just it's a high temperature process, and we have carried out successfully, and sharp crystalline peaks are noted only were noted from 7 hours 700 degrees Celsius for 5 hours heat treatment, not at 3 hours where there is a still amorphous peak, while the density have been calculated with the help of Archimedes principle, which is around 3.4. FT analysis by reflectance mode, where we are getting the metal oxygen change, metal oxygen bondings. Refractive index is found to be plotted with the Cauchy dispersion fittings. Band gap using TOC relationship, which is for 2.88 electron volt for base glass, while 2.76 value is for glass ceramides. This is in the semiconductor range. And the PL spectra is quite intense for glass ceramide sample, while it is quite weak in case of base glass. So, and finally, I want to acknowledge to INSA Visiting Scientist Program for providing this financial support. With special thanks to Dr. Atiyar Rahman Molla, the Senior Principal Scientist at CSI CDCI, for providing the lab facilities and being my collaborator. And also thankful to my university for allowing me to carry out the research at CSI CDCI Kolkata. So, thanking you. So.